So the first thing about light that we would that I'd like to tell you is that light is a small part of the entire electromagnetic spectrum. The electromagnetic spectrum is made up of 7 distinguished segments. We have divided them in terms of their frequency. I use the term frequency because frequency is a predefined, unaltered property of a wave once it's produced from the source. Depending on the medium, it can have different speed, and which can also cause a different wavelength or vice versa. But the frequency of a wave is basically what defines what that is. So we in the electromagnetic spectrum, in the order of decreasing frequency, the names go by gamma rays, X-rays, ultraviolet rays, visible light, then infrared, microwave, and radio wave. For your O-level syllabus, you don't have to remember the individual values of their frequency ranges, but you have to know the sequence itself. So in many cases, you might have some fill in the blanks or fill in the table kind of questions where you will have to fill up the appropriate position of a certain name of a certain electromagnetic wave. And all these different electromagnetic waves have different usage, which we have discussed in our earlier class, in an earlier class in the general chapter. So that is also going to be pretty important for us as well. As for light, which is a very small part of the entire visible spectrum, to which our eye is sensitive to, and using that part, we always see all the objects. One of the key information that I would always want you to remember is that we are able to see a thing because light reflects off that thing, and those reflected lights enter into our eye and they produce an image of that object onto our retina. Now in this case, the retina works as a receiving surface. So as a result, the image that the eye mechanism, the lens, optic aqueous humor, the cornea, aqueous humor, lens, and the vitreous humor, all of those reflective medium that we have is one after another. Together, they produce a real image onto our retina, not virtual image. And that real image is eventually processed by the rods and the cone cells, which are the detection for light mechanism. And eventually that is processed in our brain and we are able to see something. So to enable us to see, which many of us are gifted with this capability since birth, so we don't necessarily understand this as a privilege, a lot of things have to happen. First of all, there has to, if you want to see an object which does not emit its own light, there has to be a light source nearby. Light should fall from that source onto that object, reflect a portion of that light, and that reflection might happen in all directions for a diffused reflection that we call. So, and then it has to come to your eyes. Then your eyes should be able to detect that light. So, which means the point is important that you cannot, there is a certain threshold of visibility. I mean, zero light is something that we cannot see, but also very minimal amount of light is also something that we would not be able to see. So for example, if you come to think of it, if you think that the entire sky is filled up with billions and billions of stars, but we do not see billions and billions of stars. In our naked eye, we only see thousands of stars or something like that. The reason is that those stars which are pretty far away from us, they are also reflecting light from their own planets and maybe sending some of their light to our eyesight. But the intensity of this light or the energy amount of those reflections are extremely small. So our eyes cannot make sense of those lights. So to make sense of a visible object, to be able to see something, the amount of light that our eyes receive out of that object has to have a certain minimum value. I'm not sure. I'm not going to be giving you a numerical value, but the point that I'm trying to make is that only available light is not good enough. The available light has to be of some minimum amount of power, or energy containment is a pretty important factor for this aspect. The next thing is that, so this brings us to the idea that any single time you are about to draw a light figure, where you might draw an observer or might draw an eye, light rays should be directed into the eye, not the other way around. We are not working with Superman who is going to send out laser lights from his eyes and do something, some weird stuff. So we are talking about regular human beings. So light should be entering into the eye, not the other way around. Important bit. And then comes the basic properties. So this is one of the key things that I need you to understand. Then I'm going to start talking about the two type of behavior that we primarily teach in O-level skills. One of them is the reflection of light waves, and another one is the refraction of light waves. Reflection can be of two types. For example, I hope I can find the image. sorry, regular, not uniform. Yes. So you can see over here, this is a very simple figure for what we call regular refraction. Yeah, it's a pretty simple figure. Let's open image in tab. So have a look at this figure. Uh, Whenever light rays, parallel light rays fall onto a surface, and when they reflect outwards, they maintain a specific behavior. Now, in this case, this specific behavior is that because for the left figure, I'm discussing the regular reflection. Whenever the surface is perfectly flat, parallel light rays after reflection remain flat. So this is one example of regular reflection. However, we can have regular reflection from uniformly curved surfaces as well. For example, concave mirrors or convex mirrors. They can also give you uniform reflection. Whereas diffuse reflection happens from a rough surface. So light rays can be reflected from those portions in all the places. So another important thing that I need you to understand, that typical objects that we always see by our eye, they are pretty much all of those things pretty much make diffuse reflection, because if they made any irregular reflection, then only the person located over here should be able to see this thing, or only a few number of people should be able to see an object. Because typical objects, they all have a rough surface and they all make diffuse reflection. That's why people at different parts of the room, different parts of around you, can all see the same object, because light will enter into their eyes in all the different directions because the reflection is diffused. So that's the important bit. Uniform. So the other examples for if I just try to show you some curved reflection, where is a curved reflections? Yeah, reflection examples like these are also called regular reflection, regular reflection. So where there is a specific pattern, or you can predict in which exact direction the reflections are going to work out. For example, for a convex mirror, you have a situation like this, that the light rays are coming in from parallel light rays are coming in. This is what we call a convex mirror. You don't have convex mirror in your syllabus. I'm just telling you this because I want to tell you this, and it's good to know stuffs when you know stuffs completely. So they will be all focused onto the principal focus point. This is what you call this is the principal focus point. So this is a predictable behavior for the parallel light rays coming by. So this is also regular reflection. Or the other thing that can happen for a outwardly curved mirror, which you call the convex mirror. So the silver is over here, and so the reflection surface is this one. Parallel light rays falling onto the surface, and they are reflecting outwards, and they're going to spread out in such a way it would appear as if they are coming from this point. Now, what do I mean by this? What do I mean by this is that appearing that this is coming out from here, it would mean that if you have a light source over here, and if your eye is over here and you're looking at this mirror, you'd feel like that this light source is located behind this mirror over here. And if you make a walk along this direction, for your eyesight, it would always appear that that light source is located here. But behind this mirror, there cannot be anything because the light source is actually located here. So this is the type of images which we call virtual images. And this is the type of images that we call real images. Real images are the locations where light rays actually cut across each other and they make an actual midpoint. And those are the points called real images. And for the optical cases where the light rays spread outwards, or after the reflection or refraction, they become divergent. Have a look. These 5 light rays, after the reflection, they're spreading out in divergent directions. They're spreading out. And that kind of scenario, we cannot get those light rays to meet each other properly. So but if we extend them backwards, we can essentially get them to meet at a specific point. That is the point that we define to be a virtual point, where the light rays do not actually meet, but we can logically find out from which point they are they are behaving or appearing to be coming out from. The idea of virtual image can be extrapolated in a much, the part of the definition that I just described is exactly what is given in your textbook. So you might actually write that. You have to write that to score marks. But let me elaborate this thing in a proper way. The way our eyes look and sees thing or process the information is by what our brain tells us. So it's very easy to fool our brain by not showing us the exact thing, but giving us an illusion of that thing. For example, for example, if I just give you a simple example, it might actually make good sense. So if you have a look at this painting, I mean, this is just mind-boggling. Have a look. Oh, this is too small. Is this a bit bigger? No. This one? Yeah, this one is a bit bigger. Okay. So let me just open Imaginator. Have a look at this image. This image is practically mind-boggling. I mean, the amount of detail that is over here, it almost looks there is actually a bulb over here, but there is actually not. This person drew this light bulb with very careful observation and skill. So if you just take a normal look at this thing, if someone doesn't tell you, you might as well feel like there is a bulb. But when you really look into this thing and see these pencils and papers and there is a signature over here, you know, because now you are informed that this is actually a drawing. So our eye is feeling there is a bulb, but is there a bulb? No, there is an image of bulb. That's basically the idea of a virtual image. That's something that appears to exist there, but it is not actually there. So that's the same thing for virtual images, that whenever multiple rays, for this case, so if you stand up somewhere over here and look at this mirror to this direction, whatever these light source that you have placed over here producing these light rays, that would appear to show up here. Because light rays are going to be spreading out in this direction, our brain will tell us that from the alignment from which the light rays are coming to our eyes, that object is exactly behind that alignment. So our brain will tell us that here is the source, but actually the source is there. So that's the whole idea of virtual point, that the light rays actually didn't get there. That is also the idea for that this idea is also equally applicable for real images as well. For example, if you stand up over here and keep looking at this mirror and take a roundabout motion like that while it's keeping looking over here, whatever the object that you might have placed over here, that would also appear to show up here. So this is a real image. The reason we call it a real image, because here the light rays are actually crossing each other, whereas in this case the light rays were not actually crossing each other. So that's the basic difference between virtual images and real images. Some of you raised your hands and I went through the discussion and then you dropped your hands. Is it because that your questions are answered, or are you tired of keeping your hand raised? You can speak up. Yes, Munam, bolo.
Sir, what does the focal length mean and C stands for?
What does the focal length mean?
And C stands for?
Oh, for a curved mirror, the focal length means the distance. What the hell? Oh no.
Sir, focal length ki mane the distance between the principal focus and the mirror, curved mirror.
Basically that focal length means the distance from the mirror to the principal focus. Principal focus usually means the location where a group of parallel rays, after falling onto the mirror or passing onto the lens, it is applicable for both of the cases, they would actually meet. Actually meet is happening for a convex mirror, concave mirror, or they would appear to be meeting. Or they would appear to be meeting. So the point where a group of parallel rays actually meet or appear to meet, that is defined as the principal focus of that optical device, equally applicable for mirrors or for lenses. Whereas the C in this case represents the center of curvature of this circular mirror. For example, this is a circular arc. This mirror is not parabolic. This is a circular arc, and this is the center of that arc length. So if you draw lines from here to the center, all of those would represent radius, or they would be equal length. So or in other words, I can say that if you consider this part of the mirror was cut off from a very large circle or a very large sphere for a three-dimensional observation, then this would be the center of that circle / sphere. Muna, বুঝে গেছে?
Yes, sir.
Beautiful. Ryan Hawk, bolo.
Sir, in the case of real images, the point where all the light rays meet, that is where our brain perceives the image is, right?
Yes.
And that is also the brain perceives that is also the source of the object.
No, the source of the light is over here. The light rays being reflected off the reflection surface over here are meeting up over here. So our brain would tell us that this object exists here, because that's how we sense of objects. That from the direction, from the location, or from the alignment the light comes from, we believe that object is behind that alignment. So our brain might tell us that this object from which the actual lights are coming are currently located here, but actually it's not. Hence the whole idea of image.
So where does it perceive it to be the source to be at?
Well, if we have to look at the absolute source, we have to actually look back into this location. So the object is actually sources over here, but if you look at over here, you would see a much smaller version of that source somewhere over here.
Okay, sir. Thank you, sir.
Sure.
Sir, what is principal axis?
Principal axis আচ্ছা এটা তো মিরর দেখাচ্ছিলাম মিররের জন্য actually principal axis define করা difficult. I'll explain the principal axis when I'll get into the lens part, so don't worry about that. I'll get back to your question. I'll answer that in a bit. So moving on with the further part of the lecture. So yeah, we have Z. And then, so that's the part of the refraction that I was talking about. I mean, I have to really send a text message to someone. All right, my bad. So getting back to the idea, so that's the idea of how can I make sense of images. So if we go for the further idea for reflection, for our O-level syllabus, we only have the plane mirror and all of the implications regarding plane mirror, the image production, production and everything. So I'll be discussing the plane mirror in detail for our lecture part. So let's have a look how does a plane mirror produces an image. So let's have a look at this figure first. This one is a good figure. Yes, this one is a good figure. This is actually a solution. So, but this is an actually good figure. So have a look at this figure and let's try to make sense of it. We have an object over here. Let's say this is an illuminated object. For the sake of simplicity, currently we're starting with a point object and then we're gonna go for a vivid object or a large object. So for whenever we give up, whenever we're observing a point object, let's say this is an illuminated object which is producing light of its own for the sake of simplicity, and it is reflecting light. It is actually sending out lights in all direction. Now currently, let's say our eye is located here. So let me just copy this image and try and draw this on the MS Paint. Okay, so yeah. Let's say our eye is located here. So this is the eye. So this is one way to draw the eye. So we're trying to see the image over here in this direction. Now, what do you need to understand? Light rays would fall onto the mirror, and they're going to reflect. They're going to reflect in a way that when they get a reflection, incident angle and reflection angle would be equal, which means that if I do draw a normal, which they did draw a normal with the green line over here, but it's pretty small. So just for your reference, I'm going to try and draw a bit thicker line, the longer line, so that you can make sense out of it a bit easily. This is a bit too thick, so let's go for the thinner option. Works for me. So I just drew two normals simultaneously because I'm eating both of them. So this red light that is falling onto the mirror, that is making an angle of incidence over here, that is I, let's say, and then this one is angle of reflection. Let's say this angle is R. For reflection cases, both of these angles would be exactly equal, irrespective of the surface. Whether you have a plane surface or a curved surface or an irregular surface or a regular surface, doesn't matter. The reflection law number one is that angle of incidence is always equal to angle of reflection. So this light ray is going to be passing out over here, and the similar. And now using only a single light ray, we cannot essentially draw the image. To find out the image position, you need to find out the intersection of at least two light rays. That's why we have to draw a second light ray from the same position, and that light ray is the blue one, which is going out over here. Now, interesting point for you to understand. If I just take this part of the figure, and for your understanding, I'm gonna do something over here, which might make it a bit more understandable for you. Let's say, should I take this much bigger? No. So let's say I'm gonna take this much part. Yes, this much part. So I have a reason to take this part. I'm now gonna flip it horizontal. So have a look. I'm flipping it horizontal. If the mirror did not exist, these two blue and red light rays were supposed to go in along this direction. Because we placed the plane mirror, these two light rays simply reflected back in the opposite direction, very much similar to what you have done as transformation in your math syllabus. Did you do it? I believe so. Achha, for all of you who are asking me questions about concave mirrors, I'm not going to actually go in detail for the mirror reflection parts, I mean curved mirrors for the regular syllabus. But if you are willing to stay, you can stay after the class recording is done. I'll try to answer your questions, but not within the class period because that's not part of our syllabus. So let's get ahead. So these light rays were supposed to go in this direction because the plane mirror was placed in the path of these two light rays. They had to reflect, which means basically because these two light rays are divergent from each other, they are getting away from each other. These two light rays are also divergent. Because these two light rays are divergent, these two light rays after reflection, they will never meet at any point if we extend them backwards over here. The only way we can possibly make them to cross is if we take them upwards and eventually get over a point where they actually meet. This is that point where the two light rays, extension of these two light rays, not the actual light rays, the extension of the two light rays get a cross over here. This is the point that we call a virtual image. So whenever our eye will look up over here, it would appear that this object is behind that mirror somewhere over here. This is exactly what happens in plane mirror, that everything that you see in a plane mirror appear to be behind that mirror. But the mirror is basically a reflector surface. There is not a different world inside that mirror. You're not seeing a real thing. You're seeing the position of that object over here. And this is pretty interesting because what you need to understand that interesting in the sense that there are multiple properties that properties of the images produced by a plane mirror. One of the simple or very important properties that we'll be using a lot for our purpose, let me draw that with the green, is that if we draw a straight line joining the object and the image, we are always gonna have a perfect vertical line onto the mirror. So in this case, this is supposed to be our point. Now, whoever made this image couldn't make this properly. So there is a bit of a, it has gone a little bit up. So there is a bit of an error in drawing this image, but in all cases, this straight line will always cut the mirror at 90 degrees. This is always gonna be true. And the length of these two parts would always be equal. Or in other words, I can say that the image, so we can always say that the image and the image distance from the mirror surface and the object distance from the mirror surface, I mean for plane mirrors or any mirror, that is, image distances are always measured from the relevant point of the on the mirror. So the object distance will always equal to image distance. So this is a very useful logic which we'll be using a lot for our upcoming drawings, which I'm going to explain after a while. But let me be very clear over here that do you understand how this point came into existence? Everyone, you can unmute yourselves, and if you have any questions, you can ask me.
Yes, sir.
Can you repeat what would happen if the mirror did not exist?
The light rays would continue further in the same exact direction like this. They would not get reflected.
Okay, sir.
Sure. or the thing that I just tried to make sure that if that's the reason I copied this part, that this red light is going to continue in this direction, and this blue light is going to continue in that direction. Yes. Anyone else?
এই দুইটা
অবজেক্ট থেকে দুইটা রে আসছে, ওরা রিফ্লেক্ট হয়ে দুজন দুই সাইডে কেন যাচ্ছে, একসাথে ক্রস করে না কেন?
Because this is a flat surface. Because the rays were originally divergent, so after reflection through a flat surface, they will remain divergent. Because for this one, the angle of incidence is small, angle of reflection is also small. If you consider the same thing, that over here, let's say I can draw this with let's say another color, let's say purple. So over here, the angle of incidence is different. Let's say this is X and this is Y. So in this case, both of these angles are bigger. So this will definitely, these two light rays will remain divergent as the incoming rays were divergent in the first place.
একটু ওই পয়েন্টের এক্সিস্টেন্স সম্পর্কে রিপিট করতে পারবেন? আমি ওই অংশটা ইন্টারনেটের জন্য ইন্টারনেট প্রবলেম হয়েছিল।
কোন পার্টটা?
You were talking about the existence of a point just before you unmuted us.
I'm not sure which point I was talking about. I talked about how can we get the virtual image. That was by extending these light rays backwards so that we can get a possible cross point behind the mirror.
Sir,
Bolo.
sir, in case of virtual image, our brain concedes that the object is behind the mirror.
Yes.
Sorry about sir. Virtual মানে অবজেক্ট থেকে তো জাস্ট দুইটা রে আসছে, আরো আসছে না?
ভার্চুয়াল ইমেজ থেকে কোনো রে আসছে না।
না মানে অবজেক্ট থেকে
অনেকগুলো রে আসছে। মানে I mean, if you think of it, if you say illuminated object, this is actually sending out rays in all directions. We have only drawn 2 of those to find out the position of this one. We might as well draw a third one, but that third one will also go through here. For example, if I go ahead for that discussion, let's say I'm going to draw a single ray over here using purple. Just have a look. Let's say I'm going to draw up this ray, make it a bit thicker, okay? And then I can try to make it reflect about this position. To horizontal, and if I get this one, and if I extend extend another line from this point on this direction, you'll see that this light will also go to the same exact point. See what I mean? Which means if you even draw multiple lines, all of those rays would eventually get into the left direction. But if you extend them backwards, they would all meet at that same exact point, which is defined as the virtual image of the object. We can draw multiple lines, but we don't need more than 2 to find out the position of the virtual image. That's why we usually go for 2 only. But if you draw even more, they would all pass to this point. Except for the eye, I can draw another ray over here, which doesn't even pass to there. For example, I can try and draw another ray with orange. Okay, the earlier ray became orange because I didn't select it earlier. So let's say another ray falls up over here, and that is gonna be reflected over here. But from the logic, I can always tell you this ray is also gonna appear like this. So I must preferably make this ray dotted because this is behind the mirror. The light ray did not actually go there. So it's important that you draw the extension lines with dotted lines and the actual light rays with actual solid lines. And it's also very important to always give arrows on your light rays before the reflection and after the reflection one time. Without arrows, lines are lines. With arrows,
so
lines become rays.
And the purple line passes through the mirror.
No, I mistakenly drew it like that. The purple line got reflected, so I forgot to erase this off. My bad. Abdullah, তোমার কোশ্চেন আনসার পাইছো?
Yes sir.
আচ্ছা, চন্দ্রিমা বলো।
Sir, এখানে the object is a luminous one, right? Like it's giving out its own light.
Yes.
Sir, আমরা যদি একটা নন লুমিনাস অবজেক্টের রিফ্লেকশন শো করতে চাই মিরর দিয়ে, তাহলে কিভাবে করব?
তখন যে জিনিসটা অ্যাজিউম করতে হবে, let's assume this is a rough object, so it makes diffuse reflection, and there might be a light source located anywhere around this object. So light would be falling onto this object, and this object is going to reflect those light rays in all directions, and we can take at least two of those to make this happen.
Sir, মানে আমরা তো করব যে এটা থেকে লাইট আসছে না?
Yes.
যখন আঁকবো তখন তো we like as if light is coming from that object, not from any other source.
Yes sir.
Yes, sir.
তখন তো মনে হবে যে the non-luminous object is giving out light. সেটা কিভাবে শো?
I just become a dad. Damn. Wow. Sorry. Did you hear what I just said?
Yes.
Yes, sir.
Yes,
I
sir.
became blank.
Yes, sir.
I said I just became a
You just
dad.
became a dad.
Yes, he became a dad.
Oh my God.
Allah, actually, Allah, sir.
Yeah.
Did sir just say that?
I just said
So, বাচ্চাটা দেখি।
I don't have any picture yet. I was just informed it happened because my wife is in Chittagong, and so I'm here. And COVID is here, so I couldn't go.
Congratulations.
Congrats, sir. Congrats.
Congratulations, sir.
Sir,
Alhamdulillah. Alhamdulillah.
কিন্তু কাচ্চি ট্রিট দিতেই হবে
ডাবল কাচ্চি ট্রিট, স্যার। একটা ক্লাস 10 এর জন্য আর একটা
Without a doubt. কোভিডটা শেষ হলে
কাচ্চি ডেলিভারি করুন
কাচ্চি ট্রিট প্রচুর হবে, ঠিক আছে? ডোন্ট ওয়ারি। কোভিডটা শেষ হলে প্রচুর কাচ্চি খাওয়াবো। কোনো ডোন্ট ওয়ারি। আচ্ছা, ঠিক আছে।
পেট খারাপ হয়।
আজকে ক্লাস শেষ সবাই যাবে।
কিসের কাজ শেষ? Cope is not gonna be avoided. So any question, any further Chonima, did I get your question answered? That we might this object might not be an illuminated object for its on its own, so it might be an object that has a diffuse surface which makes up reflection in all directions. So we would essentially require a second light source anywhere around from which the object might be taking some light. We should be taking some light and make the reflections forward. So that's also possible. It doesn't have to be an illuminated object. I started with the example for an illuminated object, not to make sense with the problem, but now that you ask that, it is equally applicable for illuminated or reflective objects as well. Make sense?
তখন কি ডায়াগ্রামে একটা লাইট সোর্স দেখাবো?
না, ডায়াগ্রামে লাইট সোর্স দেখানো লাগবে না। Those light rays which are showing, they would be the light ray, they would be the light rays reflected off this object, or you can say that these light rays are coming from this object. Now, coming from the object doesn't necessarily have to mean that it was created by its own. Coming from the object means that it is coming from its own surface. So it might be its own light, it might be reflected light from a different source. It can happen either way.
Thank you, sir.
Sure. Yes. আরেকজন চন্দ্রিমার সাথে আরেকজন হাত উঠাইছিল, কে জানো?
রামি স্যার, রায়ান স্যার।
আচ্ছা, হ্যাঁ, রায়ান বলো। যাদের কোশ্চেন করা হয়ে গেছে হাত নামায় ফেলো। বলো, রায়ান বলো।
আমরা কি বলতে পারি that in the criteria of image formation, most plane mirrors and convex mirrors act in the same way due to the fact that they both form virtual images?
I wouldn't say same, but I can very much say similar.
Okay, sir.
I would not say same, but I can say similar.
Okay, sir. Thank you.
Sure. Yes, Sadman.
Sir, is it common that in question papers Cambridge give non-luminous objects?
It's usually not a very. It's not usually ever covered. I actually incorporated this discussion to give you a full idea. They would never ask you that this is an illuminated object or this is a non-illuminated object. They're going to only say it's an object. So the object is sending its light rays over here. That those light rays might be created by the object by itself. For example, a candle or an LED light or something like that. Or this object might be illuminated from a different light source, and you might have that as well. It's not essentially usually a concern for our light ray diagrams.
Sir, one more thing. Because it's a plane mirror, it will give the light rays will reflect. I mean, in a similar direction, but in curved mirrors or either convex or concave, because it's. I mean, the surface is changing. They will reflect in multiple directions.
Yes. In this case, this plane mirror is also essentially reflecting in multiple directions. It's not essentially trying to send them in a single direction. So what I can tell you, what I can correct in your question is that the plane mirror receives divergent rays and it also reflects divergent rays. Plane mirror will never produce convergent rays. So they will, it will just maintain the divergent property of those incoming light rays. That's why the only cross point is possible to find behind the mirror.
And because the light rays bend too much or too less in curved mirrors, we see objects are either too close to us or too far away from us.
hold your questions about the curve mirrors. I'll answer all of your curve mirror questions after the recording is done or the typical class lecture is finished. I'm not
Okay,
trying
sure.
to attend the curve mirror questions in the regular lecture. Ask me questions about this figure if you have any. Be pro.
Sir, what happens if the object is closer to the mirror?
Well, in that case, okay, beautiful question. This I can explain very easily like this. Did you just understand what I did?
Yes, sir.
Yes, sir.
This is what happens. This is what happens if the object is closer to the mirror. The virtual image would also get closer to the mirror.
Okay, sir.
বুঝা গেছে?
The angles like hitting the
Yes,
mirror
sir.
will just be different.
Exactly. Definitely. For example, let's say if you draw for this angle, you can see over here these angles have now got bigger compared to the perpendicular. But if I make it further apart, here the angles are becoming more acute. But ultimately, in all cases, that property will always remain same, that the object distance and image distances are always equal, and the line that we can join from the object to the image would always cut the mirror at 90 degrees. That will always be true.
Okay, sir. Thank you.
Sure. So that completes the part for a single object. Now let's go ahead and try to discuss for a vivid object, or that is an actual object, because for this discussion, I was only covering for what happens for a point object. Now, let's say if we go for a vivid object, let's say, yeah, this one is good. This one is good. Actually, no, this one is not so good. Okay, I might as well take this image. It's a bit different than the earlier one. So should I? This one looks good. Okay, I can take this one. No, I can't. Okay, that the first one was actually okay. So let's try and go for this one, and let me explain for this image. So let's have a look. Wow, this is a very big image or not. So this is consider for this one. This is a jar that we have over here, and our eye is over here. This is a flat mirror. So this is the reflection surface, and we are about to see this reflection using this reflection surface. So to be able to see this entire object, light rays from all of the parts of this object has to be reflected off the mirror and reach up to our eye. Now, for the sake of simplicity, we are only showing in this figure the image produced by two of the farthest point. One is exactly on the top, one is exactly at the bottom. We are trying to draw these two lines onto these two set of lines into our eye to find out the image position over here. So that's what we're trying to do. Check this out. This is what we're trying to do, because the idea is that if we can see the top of the jar and if we can also see the bottom of the jar, we might as well see the whole jar. So if I try to draw another pair of ray from here to here, that will produce an image over here. If I try to draw another pair of ray from here, that will give us an image over here. So for the sake of simplicity, we have to draw two set of rays if we are trying to go for an object. For a point, only one pair of rays is good. For example, here the P prime is producing the image at Q prime, where the two relevant light rays are these two, the top two. Where for the P point, which is the bottom of the jar, we have to draw this pair of light rays, which are giving us this reflection at Q. Point to be noted, to find out the image of one single point, we have to draw how many rays? Two. I'll ask you the question again. Listen to me carefully.
Two.
To find out the image of one single point, we have to draw two rays. Those two rays extended backwards would give us the position of the image of that point. And to be able to show the image of a whole object, we have to draw the image of at least 2 points, one from the very top, one from the very bottom. And those images, and together those two positions of the images can give us the whole image of the whole object. So this is the usual way take that we have to remember, which would be important for us for our drawing in the actual cases. Now I'm going to show you a much more simplified version of this whole logic, that if these kind of questions actually do show up in our exam, how easily can we work with them, or what is the easier way to draw this figure. If you wonder why am I using the term easier, let me explain this part. As per original description, the correct way or the detailed way to find out the, let's say I'm trying to find out the image of the p prime on the top of the jar. I want to find out this q prime. This I want to draw the image of this one. So let's say I have drawn two light rays over here, and as per instruction, we are supposed to draw perfect vertical over here with our protractor. So we have to draw perfect vertical over here, and then we have to measure how much is the incident angle. So let's say this is the incident angle for the first ray. Sorry, Bulaxi. I'm now drawing the top one. So this is the incident angle. Do you have a look? Let's say, let me name this ray. Let's say this is our ray number 1. Let's say this is our ray number 2. Okay, so ray number 1 is falling on the top. So I have to draw a normal over here, and then I have to measure this angle perfectly, and then I have to draw an exactly equal angle on the other side and extend this line backwards up to an unknown length. Then I have to repeat the same process for number 2, which means I have to now draw another normal. Let's say, let me draw this with, let's say, red. I have to draw another normal over at the second point, right over here, and repeat the same process. So in that case, I have to draw an incident angle, measure an incident angle over here, and draw an exactly equal amount of reflection angle over here, and that should give us the second reflection ray. And if we extend them backwards, these two rays, so let's say, let me name them. Let's say this is our 1 prime, which is a reflected ray from ray 1, and let's say this is our 2 prime, which is Bullixina. So this is a reflected ray for the incoming ray number 2. These two light rays are supposed to cross over here. Now this is usually very difficult to draw. The reason is that to be able to draw this normal perfectly, to be able to measure these angles accurately, and to be able to draw those two light rays exactly, and so that eventually their extension down the line meets up over here, is actually quite difficult, because we are susceptible, we are prone to make a lot of error in these measurements and in this drawing. So if you follow this exact procedure, in many cases, you will not get this point at the exact point that you expect it to. If you wonder, what do you expect? Drawing is supposed to drawing. Well, no, there is a logic that I just explained in the earlier figure. That logic tells us that for any of the light rays, this should be happening. That the line joining the object and the image, it should be a straight line, and they should make perfect anti-degree onto this thing, and object distance must be equal to image distance. This is the basic property of any image that is produced by a plane mirror. So the examiner is going to judge you or mark you on this logic. So if you make a mess, even a slight amount of mess over here, this point might show up somewhere over here, this point might show up over here, this point might show up over here. So it is very difficult to find out this point, locate this point exactly at this location where we expect it to. That's why there is a reverse way to draw this drawing, which is going to be easier for us, and which I'm going to show you right now. For the sake of reference, I'm going to keep this figure over here, let it be there. So I'm going to use this much space to show you what I'm trying to show you. Let's say, try to understand this part of the lecture, and raise your hand if you have any questions, and I'll give you the floor eventually. So let's say we have a vivid object over here. Let's say that object is a bit dark. So let's say this is an object that we want to draw, where we usually give an arrow symbol at the top of the object orientation, or the arrow mark represents the alignment of the object. For example, this object has an alignment, whereas this is the top, this is the bottom. And then let's say here we have an image. The question has already also, so image now. So here we have a mirror. Let's say I'm going to name this mirror surface as M prime. M prime is our mirror. And here we have the object. Let's say the object is labeled as A and B. We want to draw the image of this object. What is the easier way to draw this object? The easier way is that, other than starting to drawing your incident rays directly, we are going to use the logic by which you will be checked for your accuracy. So take your protractor out or a set square out and draw a perpendicular line so এই পর্যন্ত হচ্ছে তোমার কোশ্চেনে দেওয়া আছে এবং এখন তোমাকে বলছে এটা এই অবজেক্টের ফুল ইমেজ আঁকতে হবে and you have to also draw an eye to show where this object, how this object's image can be seen behind the plane mirror. So these are the steps that I'm recommending. So first we're going to take our protractor and draw a normal from this A point onto the mirror and extend this line such that this part is exactly equal to that part. I'm not sure if that is true, but let's assume it is true because I don't have a ruler over here, but I have to draw this line so that these two lines are exactly equal. Now I can use this straight line that I'm drawing as one of my incident rays. Have a look. If I just give an arrow over here, I can make this as an incident ray. And because this ray is falling onto the mirror perpendicularly, it's going to reflect also perpendicularly. So for this ray, what is the incident angle? 0 degree, right? So I'm drawing my first ray very easily over here, and I might as well consider to make this real line dotted, but I'm not going to make it dotted first because I want to find out where the cross point happens. And then, so once you have drawn this line to be equal, so you definitely know by now that this should be the image of the A point. So I'm giving a bit of a blob over here. Blobs are not appreciated, but I'm just giving them so that you can see it properly. So this is supposed to be the image of point A. Once you find out the image, you can very easily go ahead and draw your required light rays. For example, let's say I'm going to draw the eye with sky blue. So let's say I want to set my eye over here. This is the size of the eye that I have. So I'm going to now try to draw lines of rays so that will show how the light rays will reflect onto the mirror and get back to eye. Now, remember this previous figure. Have a look. From the eye all the way to the image position, there we have long straight lines. Do you see that? Have a look at this one, the line number 1 prime. This was a pretty long straight line. So I'm going to first draw that. How? Like this. So from, let's say, one corner of the eye, I'm going to draw a straight image over here. And I'm going to do that same thing for the other end of the eye. You can essentially make these lines a bit farther away. For example, the way there is a little bit of gap, you can also keep the gap, but gap na rakhleও সমস্যা নাই, চোখ পর্যন্ত আসলেই হবে. So I might as well give a gap. So because using a gap might prove to be helpful later on. So I'm drawing 2 light rays over here. This is still drawing. This is not final. So what I want to mean is that these two are supposed to be my reflected light. Now these two reflected light are reflected off this point. So what I can do and what I will do is I'm going to join from the tip of the object up to this point. And then I'm going to join from this tip of the point up to this point. So this is going to happen. And we have to do the necessary trimming or addition to this figure to make this acceptable by the examiners. What are we going to do? We're going to make these lines dotted because these light rays actually did not actually penetrate through the glass. And I'm going to also make this light ray, this thing. So you can essentially keep this line over here because we are already showing 2 set of light rays. So this one might not be needed, but this is the reference line which you'll be using. So, but you can do this and you can draw 2 arrows. So light rays are coming from the object and eventually reaching onto into the eye. So this will be our first pair of light rays to find out the image of the point A, which is located at A prime. Interesting point to see that I did not draw the normal and go in for the angle measurement, but I have to show that I did that, or I have to represent it to the examiners that I know what I'm doing. So what is required furthermore is that you need to draw normal lines over here, which can be like this. I'm going to draw the normal lines with pink because I can. Why not? So you might as well draw these normal lines and pull it down. And then I would like you to label these lines. Let's say I'm going to label them with brown. So what I'm going to, so have a very good look at the labeling. So here is 1 and here is 1. These 2 angles are supposed to be equal. As for the second ray, I'm giving double angle symbol with double angle symbol. Take a look. This angle means which one? This one and this one, and this angle means that one. So this will complete that drawing for one of your points. This is the most detailed drawing that you can do. In many cases, you don't have to do this much detailed drawing, but it's important that you understand the steps of this drawing. Then you have to do this entire same process for point B as well, so that you're going to have 4 different rays and you can come up with a figure like this. So point to be noted, we are not going to use the exact principle of equal angles, that we are going to use the principle of equal distance and perpendicular line onto the mirror. We're going to use this logic to find out the image position. Once you find your image position, you're going to draw the rays accordingly to complete your figure. And to make it more credible, you're going to draw the normals and eventually also label the angles, so that the examiners would know that you know what you're doing. Do I make sense so far?
Yes, sir.
Yes.
Yes, sir.
Yes, sir.
Achha, I'll take questions now if you have any questions.
Sir, object যদি irregular shape থাকে তখন কিভাবে করতাম?
আঁকা বাঁকা?
জি, like
then also we'd have to draw two set of light rays, one from the very top end of the object and another from the very bottom end of the object. We might as well have a carved object, or let's say human being. If it's a human being, we have to draw 2 rays, one from the tip of their head and another one from the bottom of their leg. আচ্ছা, এটা হচ্ছে একটা procedure, but there can be a bit of discussion that you can do. Bit of discussion মানে হচ্ছে, if we consider this one as our first light ray, try to think. If you consider this one as your first light ray, you can choose to draw only one light ray over here. What do I mean by this? এই পর্যন্ত বুঝা গেছে? Everyone?
Yes, sir.
So let me just copy this. And then I'm gonna do Control Z, 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 Z. I hope I have enough Control Z options here. Oh yeah, okay. And I would like to keep that figure, which I just copied, over there so that I don't lose it. Okay, I'm just gonna keep it over here. এটা এখানে থাকুক, এটা আমাদের পরে লাগলে আমরা এখান থেকে আবার ইউজ করতে পারবো. So these are 2 different figures. So let me just vertical line. Voila.
Sir, ray 1 and ray 2 angle of incidence is same হবে?
No.
But sir,
No.
plane mirror একটা like it's a fully flat surface, right? So
Yes.
regular reflection concept.
Yeah, so regular reflection doesn't essentially mean that it would be the regular reflection means that the reflections out of that mirror will be orderly, not random. But orderly doesn't necessarily mean exclusively parallel. Orderly can also mean equally divergent or equally convergent. That is also an order.
Yes, sir.
বুঝা গেছে?
Yes, sir.
স্যার আমরা বিসি কে ড্রয়িং করে না কেন, লাইন স্ট্রেট লাইন আঁকে না কেন মিররের জন্য?
হ্যাঁ বলতেছি আমি, একটু ওয়েট করো মনে হয়. So the other option that you can do other than drawing 2 set of rays over here is that if you consider this is one of our light rays, then we have already drawn one of the light rays. So you can in that case draw a second light ray like this and simply put your eye over here. Let's say I'm not going to put my eye over here. Let me do freeform selection and I'm going to replace my eye over here. So I can do that. In this case, I just have to complete the figure with the relevant amount of lines. So from here, let's say I'm gonna select light blue, and that pretty much can complete my figure, because in this case, well, I have to do the necessary trimming and I have to give arrows. And also I should definitely always not forget to draw the normal. Normal to অনেক বড় আকার দরকার নাই. You can draw a small normal, at least which is visible on both sides of this figure, and always use sharp pencils for your all sorts of drawing, not exclusively for your optical drawing, but sharp pencils is an essential thing. So you can only draw over here one angle sign, that this one is equal to this one. Then that is good, and that would be good enough to find out this figure. এই part 2 পর্যন্ত বুঝা গেছে কিনা? Once again, you have to understand that we have actually drawn 2 rays over here. This ray was drawn to be vertically falling onto the mirror, that's why it was falling back in the same direction. This ray was falling at some angle, that is which is reaching up to the eye. we extended these two incident rays backwards and we found out the image position. So this can also work. Other than drawing these two set of rays, you can also try and draw this much. That might also serve your purpose in many figures, which is a relevant explanation for this kind of figures. For example, let's say this figure. Have a look at this one. I'll take your questions. Just give me a bit of a time. Give me a bit of time. Oopsie daisies. এখানে তো কিছুই দেখা যাচ্ছে না। .png কপি পেস্ট করলেই ভেজালটা হয়। বুঝছিলাম। আচ্ছা, অন্য কোনো এখান থেকে একটা ফিগার নেই। Let's say আচ্ছা, এই যে চন্দ্রিমা না বিপ্র কে জন্য কোশ্চেনটা করছিল যে the light rays, multiple light rays would be coming from the object. You see, this is the real object, this is the virtual image. So you can draw a lot of light rays over here. All of those light rays will be reflected, and if you pull them backwards, they will all appear to be coming up from a single point. This is one of the figure for that question that you one of you asked me a bit earlier. You get my point? So this is that figure. That you can have a lot of light rays, but they will all behave in that manner. The light ray that I'm trying to get at is yes, I think this one. Yes, this one. So this is the figure that I was actually trying to make, but since I explained half of that figure, so I might as well copy paste it and try to make sense with it. So have a look at this figure. This is a good one. Here is the object AB. MM prime is the mirror. Wow. And A is being drawn at A prime, keeping U and V equal. So this was the initial line. You see, you see there's an arrow over here. I mean, just to get you rid of the confusion, I might as well try to move these length representations a bit far away, which would be easier for you to grasp the idea. So they will be less confused. So these arrows are here only to represent the lengths. So I'm taking a bit far up. They do not belong for our optical diagram requirement. These are just representing that these two lengths are supposed to be equal, which you would always require. So let's say I'm going to put them over here. Okay, now this should be a bit less confusing. So have a look. Shogi figure দেখতেছো?
Yes, sir.
Yes, sir.
So have a look. Try to understand the content of this question. যারা হাত উঠায় রাখো, আমি answer question নিব একটু পর। This is the AB object. From the A, one set of light rays falling on the exact point P and is reflecting backwards. This arrow represents the incident ray, and this arrow represents the reflected ray, which was extended down the line up to a random point. Basically, we already knew the position of A because we are gonna use that logic of equal length and perpendicular line. So we would know this point. And then another ray was drawn from A to Q, and that ray fell up over here, and this was the reflected ray coming to C. And these two light rays as extended backwards. So CO and AP extended backwards gives us the cross point of A prime, which happens to be the image of A. Similarly, we can have this light ray to find out the image of the bottom of the object, which is B. We have drawn one light ray along BO, which is going to reflect along OB. So you extend this backwards, and then another light ray that is BM. So you can a point name, then let's say we're going to give another name. Let's say this point is named as what? A, B, C, D, E. I might as well name this point F. So BF is the another reflected ray, and FE is the BF is the incident ray, and FE is the reflected ray. So if I extend the EF ray backwards, these two light rays BO and EF pulled backwards give us the cross point of B prime. So this can be another point. Some of you might feel like that. Is it always going to happen that we have to draw the AO point exactly at the incident point of the B? No, not necessarily. This AO point might as well be drawn over here, but ultimately if you draw the reflection of that point, you would always get it leading up to that A point. That is also very much possible. The incident point of the AO ray doesn't have anything to do with the incident point of the BO ray. They drew these light rays at the same point to avoid complicacy, to have a single point so that there is not too much mashup of multiple different points over here. But it's not essential that this point has to be equal. So you can, if you put your eye over here, let's say if our eyes are over here, we'll be able to see the image of this AB object over here. And what is really important, that this A is located at A prime position, B is located at B prime position. So the alignment of the object or the orientation of the object was same, which means if this was a person, head here and feet over here, this for the image of the person, head would be still on the top position and feet would be still at the bottom position. So your figure would be vertically upright, but it will do lateral inversion. Lateral inversion কি জিনিস সেটা একটু পরে আলাপ করতেছি, but vertically the alignment would be same. Top will remain top, bottom will remain bottom. Okay, ask me questions now. Chandrama.
Sir, if the question asks যে আমাদের eye কে observe করতে হবে, like we have to show that the eye is observing the virtual image, তাহলে কি ওই রেটা বা মানে ওই রিফ্লেকশনটা আমরা শো করতে পারি যে it's 90 degree with the mirror?
Yes, we can. That's exactly why I pulled up this figure. I mean, other than drawing this figure with two individual light rays from a single point, you can also use this vertical line as one of your rays. So what I essentially did over here, I kept one of the lines over here and used this line as my second ray. So that's essentially what I tried to show you over here. First ray, second ray, pull backwards, cross point, virtual image. You can.
First ray তে মানে যে ভার্চুয়াল ইমেজ থেকে যে আই এ ডাইরেক্টলি লাইনটা ওইটা তো শো করতে পারছি না।
না, কারণ আই তো আর এত বড় হওয়া পসিবল না। So in that case you will only gonna draw only one eye over here. Only one eye position is good enough for that purpose.
মানে for that line মানে ওই যে যেটা একদম স্ট্রেট 90 ডিগ্রি উইথ দ্য মিরর, ওটার জন্য কি আমাদের আই থেকে কোনো
না লাগবে না।
The question is যদি বলে স্যার যে we have to draw it.
No, you don't have to. If you are using this one as a light ray, you don't have to show an eye over here. But if you use these two light rays, then these two light rays should be reaching up to the eye. In this same way, you can also draw it for the B point as well. I'm going to complete this B figure over here just to make sense with you, that how can you complete that. So that might give you a bit of a better idea. Just to make my point, I'm going to make this object a bit smaller so that I do not have the same incident point. So, but before I move on, did I get your question answered?
Yes sir, thank you.
Sure. Yusuf একটু wait করো, আমি তোমার question একটু পরে নিতেছি. So let's say if B is our relevant point, I might use orange for B. So I'm going to try and draw, oops, not this one, a horizontal line from the bottom, from the B position to a possible equal length distance. For example, let's say over here. So this is supposed to be my B prime. And then I'm going to complete this. So for the light rays falling onto the B, this is my incident and reflected point, and this is supposed to be my dot line. I'm going to do the dot a little bit later because you can erase any point, but drawing is first. So this is my incident point for the light ray that is coming from the B point. So I have to use this point for one, and I have to draw one more ray that will be coming from the B point, fall onto the mirror and reflect back to the eye. So how can I do this? Pretty simple. Choose the same point that where this light ray ended and draw a straight line from this one to the B prime point. So it's the very same as this one. A bit earlier I draw this one. So this is supposed to be my line altogether, and the incident line is supposed to be this one. And now you simply erase the figure. So you erase this part because these are not real points, the real rays. They were only extensions. But also to complete the figure, you better draw the normal. Let's say in this case, I'm going to draw the normal with purple. So I'm going to draw the normal. And because these angles will be different than the earlier angles, so you should use a different sign. So if you use tick over here, you can use cross over here, or if you use single arrow, single curve over here, you can also represent these two things as a double angle sign. So this is a double angle sign, and here we have another double angle sign. So this will pretty much suffice your purpose. But this figure is not completed yet. Someone tell me what is missing.
The image.
Yeah, the image.
Okay, that's one thing. I didn't consider that. Apart from the image, what is the other thing that is missing?
Sir, arrowhead.
Exactly. That's exactly what I was trying to go for. The second thing that I'm missing was arrowheads. So you have to give arrow directions to make lines into light rays. And also, essentially, I need to draw this image over here. So I might as well draw an arrow. Can I draw an arrow with this one? Thick arrow, thin arrow. No, I cannot draw an arrow. Okay, I might as well draw a line. Doesn't matter. Thickness, all right. Straight line. So I should definitely draw the image. So this is my image, and might as well give it arrow over here. That completes my figure. Yes, Yusuf, your question.
Sir, the initial ray that we view, we view it only to show that that we are drawing in a correct way, or we are placing in the right place. But then we tweak it and make it a ray. Cambridge examiner will definitely understand this, right?
The examiner will definitely understand that, and the examiner is expected to draw in that manner, because drawing it in the exact way that we are that the procedure is supposed to work with, that equal angles and everything, will never give you this much of a good image. So you are gonna draw using that logic, and you are gonna label these angles also to make the examiner understand that you know how you are supposed to draw in the first place.
So, sir, this ray is mandatory.
Which ray?
The red one.
Yes, yes. Both. I mean, to find. Remember, that's the first thing that I explained in the first figure before I rubbed it all over. That to find out the image of one single point, you need at least two rays, which will be extended backwards behind the mirror, and they will cross themselves at a point. So, একটা point image পাইতে হলে minimum দুইটা ray লাগবে. So, for the A point, red and blue are the two rays. For the B point, both the orange lines are the two rays. So, you need two rays to find out the image behind the mirror for one point.
Okay, sir.
Any further question? Anyone?
Done with mirror?
Not yet. It's just the beginning.
Sir,
We are only seeing the tip of the iceberg. Bolo.
সেশন নরমাল যে আমরা রাখতেছি বারবার স্যার, এটা কি আঁকা লাগবে কিনা? আমি ওই নরমাল গুলো আঁকিনি আমি।
Normal gula আঁকা লাগবে to give the examiner the idea that you know what you're doing.
খুশি করার জন্য।
হ্যাঁ, these are additive, or you can say, I mean, you do not need those normals to complete your figure, because you are not following the equal angle procedure to draw your figure. You're using the other logic that the object and the image are supposed to cut the mirror at 90 degrees, and these two lengths are supposed to be equal. But you should, and you must, not should, you must represent these angles to convince the examiner, to make sense with him that you know what you're doing. This ensures full mark by all means, if that's the best way I can put this.
Sir.
Yes.
আমরা যদি নরমাল ড্র করে থাকি, তাহলে আমাদের A পয়েন্টের সেকেন্ড ইনসিডেন্ট আর B পয়েন্টের ফার্স্ট ইনসিডেন্ট এর ডিফারেন্ট পয়েন্টসে মিট করানো উচিত না, as you did in this diagram and not the previous ones. মানে মিসিং হয়ে যাবে, right?
Yes, exactly. You can draw this ray with 4 different rays like this without drawing the horizontal line like this. So you can see over here that the key difference between these two figures is what? Here they draw you 4 lines, and here I have also drawn 4 lines. But in this case, two of my rays were the single line, or were the same line, because I made this red and this orange line falling perpendicular onto the mirror. As a result, they went back in the same way. So I don't have much of a, so I have reduced number of lines compared to here. But if you don't want to do this, you can essentially do this one and repeat the same procedure for the B point as well, and you can also come up with a figure like this, which is perfectly all right. I prefer this one because this is easier to draw. Yes, but if you go ahead for this process as well, perfectly welcome, no big deal.
Yes, sir. Thank you, sir.
Sure, no problem. So if you consider the properties of images in a plane mirror, take up your book, the federal book, and turn up at page number. Can someone guide me? Look up in your page where the mirror images are discussed. Yes, I got it. You can turn up at page number 209. Let's start seeing from there. 209. Are we all there? 209.
Yes, sir.
Okay. But what you can see over there on figure 14.7, the top colored box, they're showing us the type of reflections that we have. One is a regular reflection, another is a diffused reflection. And then beyond that, experiment number 14.2 is showing us a physical proof of that logic that we use to draw those diagrams, that the object distance and image distances are always equal. So what they are doing in this figure is that they have used a graph paper where we have the grid available. They have put one of those pins onto a specific cross point of the graph paper grid lines and use the mirror, and they're trying to see where that image is behind that mirror. And now because we are using a graph paper, it's very easy to count the square boxes. For any case, you will always have equal number of boxes behind the graph paper, behind the mirror for the object. So that is a physical proof that the image is always equidistant from the mirror behind the mirror. So this is a physical experiment, which is pretty simple, but makes us to believe that why this logic that both of these lines are supposed to be equal is actually applicable. Moving on forward, ray diagrams for plane mirrors. So they have shown you over here the steps, step 1 and step 2 and step 3, and then they have gone for the vivid object. So you can see, have a look at all the figures, figure 14.10, 14.11, 14.12, 14.14. So try to make sense of these 4 figures, and if you have any question, you ask me about it. Anyone? I'm going to talk about 14.15 in a bit, but go through these 4 figures, and if you have any question, you ask me. If you don't have any questions, just say it so. Read through the description. Don't just look at the figure, read through the description and see if it makes sense.
স্যার
জি
স্যার আমরা কি সবসময় মানে দিব যে একটা পয়েন্ট থেকে দুইটা লাইট রে আসতেছে, একটা পয়েন্ট থেকে দুইটা লাইট রে আসছে, মানে টপ আর বটম,
হ্যাঁ
ওরা চারটা লাইট।
হ্যাঁ 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 For each individual point, you would require 2 light rays, at least 2 light rays to find out that its image, so that you can extend them backwards and find out that cross point. All right. Are we clear up to 14.14?
Yes, sir.
Any question?
Yes, sir. A question just popped out of my head.
Bolo.
Sir, the virtual image of this arrow we can see, does this have to be made by broken lines?
We prefer to do it that way to distinguish between actual light rays and extensions of light rays. It's preferred.
No, sir, the virtual image, this arrow thing.
Yeah, you can also draw that as draw that as a broken line. That's not essentially unclear, but your syllabus is not very specified whether, I mean, on the idea of dotted and solid lines. Your O-level syllabus pretty much prefers that if the lines are present, give the kids the mark. If they have forgotten to make them dotted, don't discredit them.
Sir?
Yes.
Step 1 এ বলা আছে যে অবজেক্টিভ সাইজ আর ভার্চুয়াল ইমেজের সেম হয়, কিন্তু যদি অবজেক্টিভ দূরে নিতে সেম সাইজটা সেম হবে না ইমেজের সাথে, নাকি
অবজেক্টিভ বুঝি না বলো।
ওখানে স্টেপ 1 এ বলা আছে যে ইমেজ সাইজ ইজ সেম এজ দ্য অবজেক্ট সাইজ, কিন্তু যদি অবজেক্টটাকে মিরর থেকে অনেক দূরে নিয়ে যায় তাহলে তো অবজেক্টের সাথে ইমেজটা সেম থাকে না।
হ্যাঁ, সেম থাকবে তার কারণ হচ্ছে what I just told you a bit earlier in the first figure that I was discussing in the lecture part is that the purpose of the mirror is to simply reflect the light rays or to make them a reflection like a coordinate line. So if you place the object really far apart from the mirror, and then your image will be also produced equal distance away from the mirror behind the mirror. So you would also see the object really far away. Your mirror will not be, a plane mirror would not be able to bring that object closer or further. All right, I'm going to start talking about multiple images on plane mirrors. You can see over here that if we use two mirrors, mirror 1 and mirror 2, I'm talking about figure 14.15. So have a look at that figure. If we use 2 mirrors, mirror 1 and mirror 2, and place them perpendicular to each other, by the combined effect of these two mirrors, we would be able to see three different images of a single object which will be placed in front of it. And in this figure, it looks like quite messy. But what I really needed to understand that how these light rays are essentially working to give you the location of that image. Interesting point. If you ever have to draw this kind of a figure, which I highly doubt you ever have to draw, you take your ruler and measure the distances from O to I1. How much is that? There is no line between across O and I1. I want you to measure the distance between I1 and O. How much is the distance? Someone.
Four centimeter. 4 centimeter.
It is 4 centimeter, right? Do you see that the 2 centimeter line is exactly the mirror position?
Yes, sir.
You can do that same exact thing for O and I2. Measure that up as well and take this out. OI1 is 3 centimeter, and it happens to be the mirror is exactly at the 1.5 centimeter mark. As for I3, respond to my questions. Questions to Parnichi. Respond to my lecture. As for the I3 point, which is produced by the combined effect of mirror 1 and mirror 2, because you can see that the light rays are reflecting first from mirror 2, then from mirror 1, and eventually reaching up to the eye. This, if you hold your ruler across O and I3, you'll see that this line would be perfectly going to the cross point of those two mirrors, or kind of like the origin, if you think this whole figure as a coordinate system. Do you see that?
Yes, sir.
And how much is the distance on both sides?
Sir, from O and I2, it's 3 centimeter.
Yes, I said 3 centimeter. We are past that point. How much is the distance from O and I3?
5 centimeter.
I'm not sure. I didn't measure it, but I can try. If you hold your ruler, you'll see that their distance is yes, that distance happens to be 5 centimeter, and yeah, that pretty much makes sense. That is 5 centimeter, and you have that origin point is located at exactly 2.5. For those of you who are wondering that what is the significance of these points, well, let me clear this up. You're having two mirrors placed perpendicular to each other, so although it's not visibly shown over here, but I'm just telling you this part, and I'm not going to show you, but I want you to think about this. By Pythagorean law, you should know 3 square plus 4 square equals to 5 square, right?
Yes.
Yes, sir.
Which we call Pythagorean triplet.
Yes, sir.
So the way the object is placed over here, that it is 1.5 centimeter above mirror 2, it is 2 centimeter on the right of mirror 1. So as a result, that distance OI2 was 3 centimeter, and the distance OI1 was how much? 4 centimeter. Now, if you try to imagine a rectangle that is produced by O, I1, I3, I2, two side lengths are 3 and 4. So the diagonal is supposed to be how much?
5.
It's supposed to be 5. And that perfectly works for any optical figure. Geometry is beautiful. Do I make sense with this figure, everyone?
Yes.
তোমাদেরকে কখনো এই ফিগার মানে তোমাদেরকে এই i3g ইমেজের জন্য যে মাল্টিপল রিফ্লেকশনস দিছে না, এরকম ফিগার তোমাদেরকে কখনো আঁকতে হবে না, but I just went through the discussion of this figure because I wanted you to have this idea that why this happens, or what is the mechanism by this happens. Yes, মানে তোমাদের কখনো এখানে i3 যে ইমেজটা আছে, i3 ইমেজটা কখনোই তোমাদের আঁকা লাগবে না. You don't ever have to draw the image i3. But I just explained this whole figure to enrich your understanding. You would never have to draw a complicated figure that is made up from two different mirrors that is not covered in your syllabus. For a single mirror, it is covered in your syllabus. So in appropriate cases, you might have to draw I1 or you might have to draw I2, which is basically the figure 14.12. So drawing the image of a single point. That's included in your syllabus. But how the image can be produced by the combination of two images, or the I3 point, that is not included in your syllabus. So it's a good thing if you understand how it works, but you would never have to draw them using the appropriate way. But then again, if you ever have to draw it, you now know how to draw it. You have to draw one line from the O position that is exactly equal from the O to the corner of the two mirrors and extend it back further down the line by the exact equal distance. Like I said, 2.5, 2.5. That gives you the position of the I3 point. See what I mean?
Yes.
We can find out the position of a single point image for a single mirror by drawing equidistant lines from the mirror up to the object and also up to the image position. That same thing is possible, but if it's a combination effect of two mirrors, you have to use that corner point of those two mirrors to find out to a diagonal through that point. Are we clear?
স্যার
Yes, sir.
তো এখানে যদি শুধু পয়েন্ট ও দেওয়া থাকে আই দেওয়া থাকে আমরা তো তিনটে ইমেজ বের করতে পারবো না স্যার
আবার বুঝি নাই পয়েন্ট ও
স্যার এই ডায়াগ্রামটা মনে করেন স্যার কিছুই দেওয়া নেই শুধু আমাদের কাছে পয়েন্ট ও দেওয়া আছে আই দেওয়া আছে আমাদের তিনটে ইমেজ আঁকতে বলছে আমরা পারবো এখানে
you can draw the image positions very easily and you can draw the rays for I1 and I2 as well because you know how to do that, but drawing the rays of I3 would be really difficult for you, like really really difficult for you. So you don't have to learn how to draw those set of double reflections from O to O all the way O to the I, which produces the I3 image. ওই ray গুলো তোমাদের আঁকা লাগবে না. But by using that logic of the diagonal distance, you can find out the position of the I3 point. That is something that you can do, but you would never have to do the drawing of those rays. No, not necessary.
Okay, thanks, sir.
Sure. So if we go forward onto the next page, I'm going to cover multiple things over here, and then I'm going to show you something if needed on the board. So keep up with the book. On the next page, page number 212, we have a lot of use for the plane mirror. The very primary use for plane mirror is to see ourselves. So for beautification and other stuffs, we for shaving as well, or just to pop a zit in your cheek, you need mirrors. weird purpose, but yeah. And then also we can use mirrors to for optical testing. You see here in the chamber of an ophthalmologist, where he might not have that much space, long space that is, but he can use a mirror, and using that mirror, he can pretty much double the amount of space that the person have to look. So what is essentially being done over here, the illuminated board behind the person is the object that the person is expected to look at, and the total distance these light rays have to cover to reach from the lettered board reflected and to the person's eye is basically double the distance of the room. Let's say I'm assuming that the mirror is placed on one wall of the room and the illuminated board is placed on the other wall of the room. So you are essentially increasing the linear distance to which the person is trying to see. So you have to understand this person will see an image of this illuminated letterbox behind that mirror, and that will be a pretty far away distance compared to what is the maximum available distance within that room. So that can happen. But there is a catch. The catch is that in plane mirror images become laterally inverted. Now this word is very important. Images will be laterally inverted. If we ever write an image, if we ever describe an image to be inverted, if you only write inverted, that always means vertically inverted. If you write an image to be upright, that always means vertically upright, which means top is top, bottom is bottom. Upright means that, and inverted means top is bottom, bottom is top. So that's important. But for the case of plane mirrors, the images are always vertically upright, but they are laterally inverted. What do I mean by lateral inversion? There's a very nice figure that I saw over here, which I'm going to pull up for the letter P. Have a look. Control V. So I take a look at this figure. So what is happening for this P? Have a look. You can see the top end of the P is still the top end, the bottom of the end P is still on the bottom end. So here the object is placed on the right side, rays are on the right side, and the image is produced on the left. For our earlier examples, we place the object on the left, which is perfectly all right. Get used to all the versions of the figure, because figures might come in all sorts and versions. So you can see that whenever we'll see this thing, the image actually gets laterally inverted. Another easier way to make sense of what do I mean by lateral inversion is that if you stand in front of a mirror, if you raise your right hand that you know to be your right hand, inside the mirror, you'll see yourself to be raising up their left hand. See what I mean?
Yes, sir.
So that's what we mean by lateral inversion. So for the case of plane mirror images, left becomes right, right becomes left. So that's what we mean by the word lateral inversion. So we have a flip in the horizontal direction. This is exactly why, coming back to the figure in your book, page number 212, figure number 14.16, that the chamber and the patient figure, you can see that illuminated board has all the letters written in their inverted form. So H is H because H is bisymmetrical, but P is distinguishable. R is distinguishable, N is distinguishable, L is distinguishable, but I is not distinguishable because I is just a vertical line. Then if you go for the bottom line, can you read those letters for the third row? What is the first one?
Y.
Third row.
C.
Third row.
E G W V
E G W V Q.
Q.
EEWGQ.
Exactly. What is the fourth row?
Y Z A D C.
Y Z A D C. What is the bottom row? Most bottom row?
O L P L P.
Egyptian লেখা স্যার
L na I.
Hebrew.
OIPSTU.
I'm not sure about the second one from the right because that looks like a 1 to me because it's not appearing to be I, neither it is appearing to be a T. So I'm not sure about that one, but for the other one, I can make sense. For example, if I read from the right, O, unknown, P, S, T, and U. Do that make sense?
Yeah.
So that's what happens. So that's one of the uses for plane mirror, that we can functionally increase the distance for the patient to check how far the patient can see. Then another purpose for mirrors is that to make periscopes. Periscopes are basically devices which we use to see blocked objects or to be at a safe location to see objects above. You can see over here what is it's a very simple mechanism that light rays from a high object is তাকিয়ে আছি তোমার চ্যানেল থেকে নয়েজ আসতেছে, be careful. So the object is located above. So light rays are coming from and falling into one mirror. These two mirrors are placed at 45 degrees with the axis of the pipe of the periscope. So after the reflection, these light rays become 90 degree reflected and it goes vertically down. So in this reflection, try to understand my point. In this in the reflection of the first case, we have one lateral inversion. And then that image or that light rays gets reflected once again at the bottom mirror. So in that case, we're going to have another lateral inversion. So two lateral inversion cancels out each other. So ultimately, the observer will be able to see the object exactly as they would have seen using their only eyes. You get my point? So top mirror একবার ইনভার্সন lateral inversion হবে, আবার bottom mirror আরেকবার lateral inversion হবে। এই জিনিসটা আমি একটু ক্লিয়ারলি তোমাদেরকে এঁকে দেখাই। Have a look at the video feed a little bit. I want to make sense with this thing, so that's why I'm going to try to show you this. Okay. Hi. Which figure should I take?
Sir, I have a question from the previous example.
No.
Okay.
Acha, bolo. I was just kidding. Bolo.
Sir, is it possible to reduce those distance using plane mirror?
Is it possible to
reduce distance? I mean, here in optical testing, the doctor increased the distance that is seen by the patient. Is it possible to reduce that distance?
by using the image of in a plane mirror? I don't think so, but I'm not extremely sure about this because I never went through the research for this question. I don't think so it's possible. That's my primary hunch, but I'm not 100% sure of this answer.
Okay, sir.
Okay, I have taken this figure for a purpose. Have a look. I'm gonna draw up one arrow over here to make sense with you. Let's say I'm gonna draw this arrow. No, not this arrow. I want to run upward direction and let this. Okay. So let's consider this is the object. I might as well make this in red, fill it up with red. Okay. So let's say this is the alignment of the object. So that this ray is coming up along this line, getting reflected off this mirror and falling down over here. So what I mean, so the reason I colored this is that when this thing will be reflected using the first mirror, it is gonna get reflected in this orientation. Have a look. So it is gonna get reflected in this orientation. Do you understand why? Because this light ray is reflected along this line, the mid-level light ray is reflected along this line, and the bottom is getting reflected along this line. So this light ray, this is how the light rays are falling. So this is how the object is gonna look like after reflection from the top mirror. Then as it's gonna reflect it back over here, once again, this is gonna appear to be exactly in the same shape. See if you can make sense of it.
Yes, sir.
Yes, sir.
So this will make the object look pretty much upright. So you don't have no problem of vision. So it will not appear that a tank is upside down. That's not gonna happen. And also it's important that here in the first mirror, we're gonna have one lateral inversion. And over here, this is gonna be another lateral inversion. So if you see a soldier over here, I'm using that idea of, I'm using the tanks and soldier examples because the periscopes are very useful equipment mostly in warfare. For example, if you're in a trench, and then you are looking out of your trench to look for where the enemies are, you can have a spare periscope, but you cannot have a spare head. So picking up with your head is not worth the risk. Do I get my point? Do you get my point?
Yes, sir. But why don't
সাকসেসফুলি উকি মারার জন্য আমাদের এটা হেল্পফুল। আর হচ্ছে যদি রেগুলার লাইফে পিসফুল ইউজের জন্য বলো, পিসফুল ইউজের কমন আইডিয়া হচ্ছে দ্যাট you can use this in safari parks to look being hiding in a trench. If you are trying to look at a, let's say look at a group of zebras and giraffes without scaring them off, then you can use that. Or we can also use this to watch some actual match while you're in the gallery and everyone is cheering, so everyone is on their feet and you're also on your feet, but you cannot see the match properly. So you can use some of the periscope to get a bit higher vision so that you can see the match pretty well. So there can be a lot of peaceful uses as well. But that's what the periscope is all about. So, and then moving onto the book for the third image, that is called blind corners. Blind corners means that in cases where, especially in the urban areas where you have buildings and everything and you have narrow roads, it is important that cars should be able to see each other if another car is coming from the other direction. In our country, we honk our horns. Honking horns is a practice that mostly is available in Southeast Asian countries. So honking horn is sort of like a communication way for us. But honking horn and the entire globe outside Southeast Asia, I believe, so far my experience goes, I might be wrong, but as far as my experience goes, that honking horn is considered as a hostile gesture. That you're honking horn at someone means you're barking at them or you're coughing them. So that's not a good practice. So for this kind of blind corners, we can install a mirror like this so that can enable us to see other people. You can see over here in an actual case, a blind corner mirror, it is carved outside. The reason it is carved outside because outsidely carved mirrors will show you a much bigger view of the whole space, because light rays can come in from a wide angle and get reflected and reach to the person's eye compared to a plane mirror. A plane mirror's view of angle is exactly the same as the incoming rays, where our carved out mirrors can give you a much wider view. This is also the reason, for those of you who have seen this, that in the side mirrors of motorcycles or cars, it is always written that objects are closer than they appear. Have you ever seen this notice?
Yes, sir.
Concave or convex?
Those mirrors are slightly convex. Convex means they are slightly carved outwards so that you can get a better, wider view of the road, so that you have more information. other than using a plane mirror, it is curved a little bit, not so much as this one, so that you get a wider view of the same. But whenever you do this, the image actually the images of the objects appear to be smaller. Now we essentially make sense of objects from our experience and from their size. For example, you know how big a provost car looks like. So if a provost car is close to you, you're gonna see a bigger view of this thing. If a provost car is far away from you, you're gonna see it to be smaller. So in your mirror, you will see them smaller because because of the shape of this mirror, make the image slightly smaller compared to the actual object. Why does that happen? I'm not getting into that part in our lecture, but take my word for granted for the timing that the image produced is slightly smaller than the object's actual size. So our brain might tell us that, well, it looks small, so it is pretty far behind me, so I can actually make a sharp right turn. But that might not be the case. They might as well be on your neck, but in the mirror, they might appear to be slightly smaller. Make sense? Okay. That was the part for the reflection part. There is one part for the reflection chapter that I did not cover, which I'm going to cover. And I might call it a day because I can actually start the idea of refraction as from fresh start from tomorrow, which is, if you please go back a little bit and take a look at page number 8 and have a look at the 2 laws of reflection, page number 208. Go back.
Sir, I went back.
Good. So have a look at the first law. What does it say? The incident ray, I mean, there is no significance of the sequence. You can name one of them to be first, the other one to be second, doesn't matter. But one of the law that I have already used and explained in our discussion, which was I equals to R, which is labeled as the second law over here. The first law reads, the incident ray, reflected ray, and the normal to the surface all lie in the same plane. What this means is that, have a look at the board. Let me explain this idea. If I draw a very simple plane mirror, let's say here I have a simple plane mirror, black, thicker. Okay. If I draw a simple plane mirror, an incident ray falls onto the mirror, let's say that is red over here. So this will make a certain angle with the surface. So try to visualize this in a three-dimensional plane, in a three-dimensional thing. So here would be this thing, and you can draw a normal onto this point that might as well appear like this. Let me draw this with blue maybe. And then the reflected light would be, let's say, green. So let's say this is the incident ray and this is the reflected ray and this is the normal. So we know that this logic is already clear, I equals to R. So what does this idea of all of these three things lie in the same plane? Try to visualize this in a three-dimensional view. So consider this mirror has a shape. If you look at this setup, this is already happening, but if you look at this setup from this side, so I'm gonna try to show you the bottom of the mirror. Let's say in this case, whenever you're looking from this side, when you're looking from this side, I might as well consider to make this figure. So so consider this scenario. So let's consider that we are looking at this setup from this orientation. So if I try to draw these three rays looking at the mirror from this position, let's say now this is the side view of the mirror. So let's say this is the other side of the mirror, and this incident ray is being drawn as a red ray. So this is the mirror, and let's say this incident ray is over here. Let's say this incident ray is over here. Do you get my point? How am I doing this thing? What is actually happening here?
No, sir.
Sorry, sir. Red line and incident ray.
The red line is an incident ray. This is a side view. This is the side view of the setup. This is the front view of the setup, and this is the side view of the setup. So I'm drawing the side view of the setup. So you're looking at this setup from this direction. Let's assume these lines actually exist. So let's say this red line is shown up over here as the incident ray that is falling onto the mirror at this point. So this is that same point. So the mirror is not actually a line, it is actually a plane. So let's say this mirror was as big as this much. Let's say this is the actual mirror. So when you are looking from the side, this edge is this line. That's what I'm trying to mean. See if it makes sense.
Yes, sir.
Because so if this is the incident ray alignment, the normal and also the reflected ray, they would all be behind this line. You cannot have the normal appear to be like this. This is not going to work. Or maybe the normal appearing like this. This line, and this line, they will all remain on a vertical plane. Let's say that vertical plane might as well be something like this. So I might as well make this vertical plane like this, passing through that level. So yes, something like that. So it doesn't look much like a vertical plane. So this is what I mean. So all of these three lines should exist on the same plane. This is the first law as per the book. So these three lines cannot be on three different alignments. They will always have the same alignment compared to each other. Do I make sense? So this is not going to happen. This is the wrong thing. This is not going to happen. All of these three lines will be overlapping with each other. For example, so that would mean that this red line, blue line, and the green line, they would all be aligned properly.
Sir, it means that the red line will block the image of the green and blue line.
Yes, if you consider the lines as physical objects, answer is yes. Yes.
Okay, sir.
Any question? Anyone?
রাইট সাইডে ওটা কি নরমালের পজিশনটা দেখিয়েছেন?
No, the red line in this case is showing you the incident ray. The normal should be behind that incident ray, and the reflected ray should also be behind that reflected ray. So this blue line should not exist. Behind this red line would have the blue line, and behind that blue line we should have the green line. They should all align in a single line, single plane.
When looking at from a side, right?
When looked from the side, exactly. বুঝা গেছে?
Yes, sir.
Yes, sir.
Kids, thank you very much. I told you that I would take your questions from curved mirrors, but I really cannot because I have a lot of communication to do depending on the recent incident that just happened. I'm extremely excited for this. So I'm closing the class for today, but keep your questions in your mind. I might as well entertain them later. Thank you very much. Bye. Good night.
Bye bye, sir.
Bye bye.
So trying to limit the class. Bye bye.